Good morning, everybody. I think, afternoon. Good afternoon. My name is Zakes, and I'll be taking you through the black sheep of the family of the paper writing process. Because realistically, what people do is that you write your whole paper and you forget about experimental. At the end, you submit to your supervisor. That's when you start thinking, oh, what did I do? And what was the XPS like? And what was the temperature? And what was da. And then you go to a paper, you find out who did the same thing with the same experimental details as you copy that, you put it in your paper, and then done so. Right? That's normally how it goes. But there are really some critical factors about how to write an experimental section. This is essentially a core of what it means to be somebody who is a scientist, right? Because it's part of the scientific process, the scientific method, right? So first of all, great, right. So we've spoken about the introduction, right? The introduction normally represents the why of the paper writing process. So what we want to understand is, why are you conducting the work that you're conducting? Why is this work important? Why should anybody care about whatever it is they're going to read about in the next 5, 6, 7, whatever pages, right? So when we get into the experimental section, we're actually talking about the how. So the question is, how did you do the things how did you conduct your study? How did you achieve whatever objective that you wanted to make, or how did you reach the conclusions that you reached in the particular study that you conducted? So I think the important thing here is that essentially being a scientist is kind of like, you eventually realize that it's like being an author, and being a good writer is part of that process, right? So Dr. Ella yesterday talked about some of the core aspects of building a narrative, right? Of having to keep your audience engaged while also being informative. So what you want to do is, like, I want you to listen to what I'm saying, right? But I also want to be as informative as I can, right? So it's part of that creative but technical thing. It's an extremely critical skill. So what I want to do now is this show that I really like called The Ozarks, right? And it's about laundering money, right? And then this guy essentially goes through the process of how you do that, how you launder money. So I'm just gonna say this.
Say you come across a suitcase for $5 million.
If you can hear this.
A yacht, a mansion.
Oops. I'm hoping this is going to be audible.
Money laundering 101. Say you come across a suitcase with $5 million in it. What would you buy? A yacht, a mansion, a sports car. Sorry, the IRS won't let you buy anything of value with it. So you better get that money into the banking system. But here's the problem. That dirty money isn't clean. Looks like it just came out of a bank vault. You gotta age it up, crumple it, drag it through the dirt, run it over with your car. Anything to make it look like it's been around the block. You need a cash business, something pleasant and joyful. You mix the $5 million with the cash from the joyful business. That mixture goes from an American bank to a bank from any country that doesn't have to listen to the IRS. It then goes into a standard checking account, and voila. All you need is access to one of over 3 million terminals. Because your work is done, your money's clean.
Okay, so unfortunately the audio wasn't that great, but what he's essentially talking about is that if you walk around the street and you get a suitcase that has $5 million in it, what do you do if you want to get that money to be clean, right? You can't just go into a place like, I'm buying a house. Obviously that would need to be reported to SARS, right? So you take it, you need to actually crumple it up because it can't look clean, right? It has to look used. So you run it over with your car, to make it as dirty as possible. Then you go to get a cash business where you could actually put your cash money into that business and then report that as revenue, and So it goes through that entire process. The interesting thing is, though, if you listen to him, and then by chance right now you walk out and you find a briefcase with $5 million, I'm pretty sure you'd be caught within a week. I'm pretty sure that we'll be seeing you in jail the next week. Because even though you have an idea of how to launder money, you don't actually understand the actual details and steps of how to do it. So in a movie or in a book or whatever, what they do is try to give you a good enough idea for you to understand what you're doing, because it's a narrative device, right? But they're not going to give you the proper details of how to replicate that. And that is the most important thing about a scientific experimental. Everybody needs to be able to replicate everything that you do in that paper. Everybody. So it needs to be very, very easy to do again, which is an interesting thing, because from everybody here, if you've ever tried to replicate an experimental process from any paper, you'll know it is a nightmare. Right? You barely ever get what they get. And you're like, but I followed it. I followed everything you did. But I didn't get the thing that you wanted. So your star-shaped nanomaterials, whatever, you did it and it comes out as a huge blob. Right? That's normally how it goes. So what I wanted to put forward is that an experimental is essentially a narrative device. It allows you within the story of your paper to tell people how you did what you did. The only difference with it being in a scientific context is that it needs to be extremely detailed for the purposes of replication, right? So, right. So the purpose of writing an experimental obviously is to tell people how you did what you did, but it also serves two objectives. First is to verify the validity of your findings. So if I'm a scientist and I'm reading your paper, I want to be able to test or to see whether or not the things that you are proposing are probable, right? So if you go into an experimental section and somebody is saying, oh, I'm synthesizing silver nanoparticles, and maybe they said in one reaction mixture, I had a capping agent, and in another reaction mixture, I didn't have a capping agent. And then you go to the results, the one with the capping agent has a larger size than the one without a capping agent. That doesn't really make any sense, right? So if that person actually writes the experimental section in that way, and the results are conflicting with what they did in the experimental, that's how you can catch. But if you don't explain what happened in terms of how the one with the capping agent had a larger size, it's logically inconsistent. Right? So if if you submit your paper to your reviewer, they would ask me, okay, can you please elaborate on how this happens if you did 1, 2, 3, 4, 5, right? The same goes if you are maybe making something like copper oxide, using a tube furnace. You take your copper chloride, you put it in your tube furnace, but you flush argon and nitrogen, right? But in the end, you're saying, I made copper oxide. My question is, but there's no oxygen in the system. You are flushing with argon and nitrogen. It's an inert environment. How did you make copper oxide? So that now, I'm essentially trying to validate whether or not what you're saying is probable, that it makes sense, right? So another thing that you want to do is you want to see if whether these things are replicatable, right? Most important thing is to be able to replicate. How do you determine whether or not the findings of somebody are true, right? The best way to do that is to replicate their work. If you're telling me, oh, Zakes, I've gotten this incredible method that makes me make gold out of lead. I'm like, oh my God, that is incredible. I want to see if this works. And you're like, I want to sell you that method for $10,000. Right? The first thing I'm going to say, okay, I want to replicate your method first to see whether or not what you're saying is the truth. And then I'll be able to buy that method or process from you, right? The problem in the scientific community is that this practice of being able to replicate each other's work has kind of fallen away. So what you normally have is that maybe Butler will write a paper, right? And I'll look at it and I'm like, oh, cool, this sounds nice. And then, boop, there it is. Move on to the next thing, right? But logically, I have no idea whether what she actually wrote is true or not until I'm able to replicate that myself, or until enough people have replicated to prove that it is actually correct. So this is two of the most important objectives when you're writing your experimental procedure. So some of the general principles for good practices when writing your experimental procedure is to be clear and concise. One of the most annoying things about reading like a procedure, right, is that people can be very vague in how they did the thing that they do. Right? Say, oh man, I synthesized these gold star-shaped nanoparticles, right? Sometimes researchers can be deceptive, right, in the processes of how they made those gold star nanoparticles for the purpose of holding on to that method for later, right? Let's say I'm the first person to ever make gold star nanoparticles, and I'm thinking, actually, I could got 3 papers out of this, really. I could get the synthesis paper, wait a little bit, synthesize again, application, maybe a second application. But if I publish the full synthesis procedure and you see it and you get to the application before I do, I just lost a paper, and that might be significant. So a person, right, would maybe have done, I drop-wise added sodium hydroxide into the solution. That may be what they actually did. But what they write is, I added sodium hydroxide to reach a pH of ... Right? It's leaving a very important, significant detail for you to replicate that work. So technically, I mean, you told me what you did, but there's no way for me to replicate exactly what you got, right? So people will try to be vague and kind of massage it such that, I mean, the editor can be like, okay, it's acceptable enough, but whether or not you can replicate that is a different issue altogether. The second thing is that your experimental needs to be well organized. So normally it would follow a typical structure where you have your materials and reagents, where you're like, these are the chemicals that I use, this is the purity, ... The second part would be your equipment that you use and the specific parameters that you use when you are running your experiment. I was running XRD, this is the 2 theta range that I was looking at, this is the temperature that was running at ... The next thing is where you put in your special conditions, right? The special experimental conditions that are very unique to your work. So if I'm doing hydrogen evolution reaction, what I'm gonna put is my hydrogen evolution reaction setup. It's a 3-electrode cell. The reference electrode is your silver chloride. The working electrode is this. This is how I drop cast it ... If it is maybe say so perhaps, he's going to say computational methods, and he's going to put all the computational methods that he used to produce his result, right? So that would be different depending on what it is that you're actually doing. Obviously, like we said, you need to be transparent, right? You need to document everything, right? So that you can actually put everything in your experimental procedure, which then talks about the importance of having a book, right? An experimental book. I know when you started, whether you're doing master's, PhD or whatever, your supervisor would say, please take your book and write all of the experimental procedures in your book, and then you did it the first day that you tried to do the experiment and then you forgot about it. I think if we went back and looked at all the experimental books in the lab, probably 2 pages, maybe. Anything beyond that is just blank. Because you think, I made it and I know in my head how to make it. So whatever, right? But this is super important because it allows you, when you're writing your experimental procedure, to know the exact thing that you did, which is very, very crucial. And also another thing, for some of these like high impact factor journals, one of the ways that they're able to verify that you actually made the thing that you made, right, is to actually check your logbook. Because you put in your logbook, you wrote your experimental conditions, you wrote the dates. So if I come and say, oh, you said you made gold stars at this date, ... I can go to your book and be like, okay, at least you have some kind of record to prove that you've done the work. Right? Okay, so another thing is that you need to be specific, right? It needs to be super, super specific. If you're saying, oh, I'm adding a specific amount of copper chloride, right? You can't say, I've added some copper chloride into the reaction. I'm like, what did you add? 0.1 milligrams, 0.1 microliters, what is in that thing, right? That is a very crucial detail. I think if any of you guys have ever tried to scale up a colloidal process and you started with your 0.1 milligram, right, and you start to put 0.4 in the next reaction, tell me if you get exactly the same thing that you got before. It's a very important thing for you to note what is the exact amount that you actually put into your reaction. Another thing is that it needs to be detailed, right? You need to put in as much detail as possible without, what can you say, without being redundant. So essentially put all the information that is important without repeating what you put in. So you can't say, oh yeah, well I've added 0.1 milligram of that, and then in the next 2 sentences you're saying the same thing. You want to be detailed as possible so I can read and be able to understand what you're saying without giving me too much information. Right? One thing that I've seen in publications is that somebody will write an experimental section, right? And they will write it word for word. I did this, I did that, this is what happened, And then below that, they will put in a schematic of what they did. Oh, this is a schematic of what I've done. I'm like, why are you putting in a schematic? You already told me what you did. So why are you putting in a root by root schematic of something that you already told me? It's either you put in the schematic or you tell me in words what you did. And if you are putting a schematic, which is what happens in publications a lot, people will then forget to put in the particular details of what they did. You can't put, yeah, this is a watch glass with some powder on it, this is nickel chloride. How much nickel chloride? What stoichiometry of that nickel chloride is that? So these are the details that you need to put, whatever format that you use to write your experimental section. Another thing is that you need to use past tense, right? So you're not gonna say, I'm walking into the lab and I'm doing this and I put the what into the what. It has to be, the reaction, the copper chloride was added into the reaction mixture that contained ... right? So this is just, what can I say? It's a general principle on how people write experimental procedures. I think that Dr. P already alluded on past tense, active voice, passive voice, ... So that's part of the process of writing an experimental procedure. So the typical structure of experimental procedure, like I said, will have your materials and your reagents. So this is the detailed list of all the materials that you use and the reagents that you use in your experiment. The second thing would be the instruments and the equipment. So this will be an overview of all the instruments that you've used in your experiment and the very specific conditions that you used while you were conducting that experiment or that characterization. The third thing would be the method and procedure, and this is when you detail, I added what into what, and then I put this in whatever it is, and I dried it when I was finished. So it's the step-by-step, very detailed procedure on exactly what you did. So the fourth would be then, like I said, your special conditions for the particular application or whatever it is that you're doing. If you're doing computational methods, you tell us the program that you use, you tell us the parameters that you put in there to generate whatever data that you're generating. If you're doing electrochemistry, you tell us about all the electrodes, the kind of cell that you are using, right? So for materials and reagents, this is what it would normally look like, right? The first thing that you're going to have is the name of your reagent. So you're going to put in, well, I have nickel chloride tetrahydrate. And then you need to put in the chemical formula of the chemical that you're using. So I need to know, right, are you using nickel 2? Are you using nickel 4? Because I'm assuming that the oxidation state of whatever metal that you're using matters in the reaction that you are conducting. So this is a very important detail. Not only that, I mean, the structure of the materials, depending on the chemical formula, can be different, right? So that is a very important detail to add. Another thing is the purity. So you know that in your chemicals, right, you have your technical grade, reagent grade, so on and so forth. An interesting thing here for the people who are using olelamine. Olelamine is like, what, 70% olelamine? Do you know what the other 30% is?
No, they don't.
Nope. Nobody knows, right? That is an important detail, because now, how do I know that your 30% whatever that is in the olelamine is not affecting the result that you get, right? So even if you do not know how the interaction of the 30% impurities creates the result, at least you've told me that it's 70%. I need to know that it's 70%. And I'll give you an example. There's a guy that I was working with, who was working with Dr. Juanita, and he was making titanium complexes. So he wanted the titanium, which was connected to a sulfur, and he wanted to make titanium sulfide, right? So when I was like, okay, you just take olelamine, you put your complex there, and boom, you get your titanium sulfide. And no matter how many times he did it, he would always get the oxide. So he was like, yo, dude, what is the purity of this thing? I'm like, it's 70%. I'm like, so what's the 30%? I'm like, I don't know. So now that's a question that you need to answer. Why am I always getting titanium dioxide instead of getting the titanium sulfide that I want? Are there impurities then playing a role in what I make? Those are the questions that need to be answered in your discussion, right? So the next thing that you need to put in is the source of whatever chemical that you're using. So you put Sigma Aldrich. Well, Sigma Aldrich and Merck are the same thing, yeah? Sigma Aldrich, does BASF make chemicals? Yeah, those ones. You know, some of them are very specific to the country that you're from. So they'll say, what Korean chemicals company, ... right? So you need to be able to trace the exact source that, especially, right, this is another example as well, is that if you've ever tried to essentially purchase a chemical from Sigma Aldrich and purchase a similar chemical from a chemical company in South Africa, you will know the differences. In fact, sometimes you can see with the color. I think there was some point when Digo was getting silver or gold, some gold salt. You would get a gold salt from Sigma Aldrich and it's clean, beautiful color. Get one from South Africa, it is a brownish tint. What is the brownish tint, right? So another thing that you want to add is how the reagents were used. So normally at the end of your materials and reagent section, they will say all these chemicals were analytical reagent grade and were used as purchased. So if you do purchase oleamine from Sigma Aldrich and you say, okay, it's 70% and I don't like that. I'd like it to be as pure as possible. And then you take that oleamine and you purify it to be 98%. You would need to say that, okay, I got it, 70% oleic acid, or oleamine, whatever, and then I purified it to be 99%. So nobody is going to assume that you did anything to whatever chemical that you got, right? You need to state that you made modifications to that particular chemical. Another thing that people add sometimes is catalog numbers, right? If you go to Sigma Aldrich and you want to buy a chemical, they normally have a specific code that is tied to that chemical, right? And a perfect example of why that is important is that I think I was buying some chemical in Dibo, and this chemical was essentially dissolved in different kind of solvents. So there was one in water, one in THF, one in dichloromethane, right? So you would think that, oh, well, I mean, regardless of whatever solvent that this thing was dissolved in, it should be the same thing, right? But not. That may not necessarily be the case. What if one of your reagents is hydrophobic and you have some chemical that is dissolved in water, right? How does that interaction change the product that you get at the end? So these are some of the things that you need to think about. So the second part would be your instruments and your equipment, right? So here you'd essentially detail first what instrument you use, powder, X-ray, diffractometer. You'd need to talk about the manufacturer, right? So you used a Broca D8, or you'd use maybe a Rigaku, Miniflex, whatever. So you just detail the manufacturer and that manufacturer, the particular instrument that you're using. And the most important thing, in my opinion, you need to state the parameters that you use to obtain whatever data that you obtain, right? If you are using maybe a diffractometer, we need to know whether or not you used a copper source or a cobalt source, because that essentially affects the kind of powder pattern that you get and the shifts that exist within that powder pattern. Another good example is when you're doing a specialized technique called grazing incidence diffractometry, is that what you call it? When you look at thin films, what you do is essentially make very low angles to your goniometer, right? To make sure that the X-rays essentially just graze the surface of your sample and you're able to get specific information about that thin film, right? If you essentially increase those angles, right, you penetrate deeper into the sample and then you wouldn't be able to report anything about the surface characteristics of your material, right? So that's a very important thing to consider. Another thing is that you can put in the country of origin. most of the time I think that this is an unuseful detail, unless somebody can explain to me why this makes sense to you. Maybe broker decided, now we want to outsource our machine to China, outsource manufacturing to China, right? And your differential that you got from China is giving you a different result from the one that I got from Germany. It could be a possibility, but it's very, very unlikely. So now this is the process. Sorry, I didn't put in the right heading there. So this is when we come to like the process of what you do when you're making your materials, right? So for this, you have to again put in like what the reagent that you're using is. You do this obviously step by step. I added this, I did this, I did this, exactly as you have conducted the experiment. You would put in exact concentrations. So if you put in 0.05 millimoles, you need to say 0.05 millimoles. You can't say, well, it was kind of like between 5 and 7 millimoles. There's no kind of, but it was maybe approximately like this. It has to be exact numbers. That is the amount that you actually added. And this is the same for exact volumes, right? So now this calls into question the way that people put in like the volumes when they're doing colloidal synthesis, and you're looking at your cylindrical, your measuring cylinder, and you're like, hey, it's kind of 20, right? Is it 20, 25? You need to put in the exact thing that you're actually using. Another thing is to do exact temperatures. This is tricky for us, right? Because what we normally do, right, with the, the heating mantles that we have in the lab, is that you don't have a thermocouple that will keep the temperature steady at 320 degrees. So you are looking there, oh, it went to 340, go back, and then 320, oh, it went to 280, then you put it back to. So the question is, right, which is what I asked Prof once, is that what is the effect of that and how do you report the temperature? So the argument for me still sits, do I say that this is the temperature that I wanted is 320 degrees, or do I actually say what really happened and say the temperature ranges between 310 and 3 whatever, right? So that is a question. I think that you can ask it, what he says, but in my opinion, right, it's better to be truthful and report the range that you actually use. Because if you're not using a thermocouple, for instance, if I'm like, what heating mantle, if I'm reviewing your paper and I'm like, what heating mantle did you use? I know I use this heating mantle. And then I go online and I check, but this heating mantle doesn't have a thermocouple. How did you keep the temperature at 320? There's an issue now. You must explain. Anyway, so, right, this is the same with the times, right? So, in the lab, I don't know if they still do this. We used to do this time studies, right? Where, oh, the reaction is happening, I'll take an aliquot, and go test what that looks like. I'll take an aliquot and go test what that looks like. And then you're sitting in the lab, somebody calls you, you forget a little bit, and it's not 15 minutes anymore, it's 17 minutes. But when you report on your report, you're saying, it was 15 minutes. That creates an issue. So now you're like, but I don't want to repeat this thing again. But at least you'll be like, okay, I didn't take a measurement at 15. I took it at 20. Because that is an honest description of what you actually did, right? So another thing, make sure that everything is in chronological order, right? It's important for you to say everything that you did. For instance, right, for the guys again who are doing colloidal, I'm sorry, I do colloidal a lot, so it is what it is. So when you do sulfur and selenium, right, they thermally reduce at 220 degrees, right? So it starts black or yellow or whatever, and when you get to around 220, it changes color and it becomes orange or whatever it is, right? If you tell me, yeah, I added cobalt chloride to the selenium, when? At which point did you add it? Did you add it before it thermally reduced? Did you add it after? Does it affect your result? I need to know what exactly you did so that I can trace if in the XRD I go and I see, really? If I go and see impurities, right? I can actually test and go back, well, may have not thermally reduced before you added your metal precursor, and that's why you're finding impurities of unreacted selenium in your system. So this allows you essentially to keep a track of the things that could have happened in your experiment and how you can explain what is happening. So again, like I said, there are specific procedures that you would use depending on the application that you're doing. I think the examples that I've made, if you're doing electrochemistry, you put in how you drop casted onto your electrode, what exact measurements did you use, what reference electrode did you use, and how did you correct from silver chloride to RHE perhaps. All of those details need to be put into the paper. Another thing, I think this is something that was done by Dr. Arthur, right? If you're doing any specialized experiments, using your TEM, your XRD or whatever, you need to actually explain what you did, any modifications that you made to the experiment itself, any special modifications that have been made in how you process the data in terms of your programming and the software that you use. All of that information needs to be included in the paper. Same for grid field refinement. You need to say this is the particular program that we used, ... right? So I'm actually done. Okay. Cool. Anyway, right? I wanted to do a little fun example, Nyana, and then we'll go on to the activity. So I went to ChatGPT and I was like, give me the worst experimental procedure you can give me, like a really, really bad one. And I'll read a little bit of it to you. So this person was like, we did the experiment in the lab last month and used some chemicals. First, the solution was made by mixing stuff, and then it was heated at some temperature for a while. After that, things were added and left for a bit until something happened. We got a color and then measured it. Some instrument was used, like a UV thing and maybe a microscope or something. The pH was checked sometimes and it looked fine. The samples were dried on a bench, or maybe it didn't happen, not sure. There were 2 samples, maybe 3, and they were compared using the machine. The results were put into Excel and then we looked at the graph. Some data was bad, so we didn't use it. Also, the temperature was not controlled, but it was around 222 to 30 degrees. The electrodes were fabricated by putting the paste on a thing and drying it for a while. Sometimes it worked, sometimes not. We tried it a few times and chose the best one. The concentrations were like 1 or 2 milligrams per milliliter, maybe higher for the other. No statistical analysis was done because it looked okay visually. The results showed a peak that was interesting. More tests are needed, but we think it works. Dope. So this is close to perfect, man. You can't get better than this. So this is like one of the worst that can be produced. Something like this obviously would not even go near a publication. But what I've done, I've brought copies of something that looks close to the perfect thing, but there are some errors in it. So what I want to do is maybe you can look at that and see if you can spot any errors in that one. Is that cool? So you can organize yourselves in your groups, and I'll hand out the experimental procedure. Oh, is Grace here? Oh, actually, I thought it was Q&A first and then lunch. Sorry. Oh yeah, any questions? Any questions? Yeah?
I wanted to ask, you know how in papers, like you said, in papers you find different units of measurement, right? Some of them report in millimolars, some of them report in grams, some of them report in the concentration. Do we have a standard publication?
I don't believe that there is a particular standard that we use, but the most important thing is to be consistent.
Yeah.
You need to be consistent. If you're using millimoles, you must use millimoles until the end. If you're using milliliters, you must start using milliliters until the end. You need to use milliliters, right? I think this is one of the problems that Prof used to be annoyed by, because somebody would be like, well, it's hour and your denotation was H, and then later on it was HRS, and then you change back into H again.